Hey everyone, and welcome. Today, we're going to tackle one of the absolute best tools you have in your integration toolkit, and that's partial fractions. We're going to break down exactly how you can use this technique to solve integrals that look, well, seriously complicated, and we'll be focusing on exercise 8E from the textbook to really nail it down.
All right, let's just jump right in. So how would you even start with something like this? I mean, take a look. At first glance, it's pretty intimidating, right? You can't just use a simple substitution, and it's definitely not one of your standard forms. This right here is the perfect example of a problem where partial fractions are going to be your new best friend.
So, here's our game plan for today. First, we'll look at the integration challenge itself. Then, we'll unlock it with partial fractions. We'll do some guided practice with worked examples, and then move on to mastery with the textbook exercises. After that, a little final test with some exam questions. And by the end of all this, you're going to have a brand new integration superpower. Let's get started.
Right, first up, the integration challenge and the tool. Before we start crunching numbers, it's super important to understand why we even need this method. You got to have the right tool for the right job.
And that tool, of course, is partial fraction decomposition. The whole idea here is pretty simple, actually. You take a really messy, complicated fraction like that first one we looked at, and you just break it apart. You split it into a sum of much, much simpler fractions. And the beauty is, each of those little pieces is something we already know how to integrate, right? They usually just turn into a natural log or a simple power function. It's the classic divide and conquer strategy, but for calculus.
Okay, theory is one thing, but let's be real. Seeing this thing in action is where the magic really happens. So let's walk through a couple of foundational examples. This will give you a feel for the different kinds of situations you're going to run into.
So for our first example, check out the denominator here. It's a bit of a mixed bag. We've got a nice simple linear factor, the x plus 1. But then we have this x squared plus 3 term. Now that's what we call an irreducible quadratic factor. Basically, it means you just can't factor it down any further. And when you see one of those, it needs its own special setup for the partial fractions.
Okay, so the setup is absolutely key here. The linear part, x plus 1, that's easy. It just gets an a on top. But the irreducible quadratic, x squared plus 3, that needs a full linear term on top, so we write bx plus c. Now the fun part, solving for a, b, and c. We can be really clever here. If you let x equal -1, watch what happens. The whole bx plus c term gets multiplied by 0 and just vanishes. That immediately gives us a equals 1. So cool. Next, setting x to 0 is always a great move, which helps us find that c equals 0. And once we have a and c, we can plug in any other simple number for x, like x equals 1, and that'll give us b equals -1. So now our integral is split in two. The 1 over x plus 1 part, that's a piece of cake. It just integrates to ln absolute value of x plus 1. The second part, negative x over x squared plus 3, needs a little more thought. You got to look for that f prime x over f of x pattern. The derivative of the bottom is 2x. We have negative x on top, so to make it match, we just need to pop a -1/2 out front of the integral, and boom, it becomes -1/2 ln absolute value of x squared plus 3. It's a perfect example of how you can break a tough problem into patterns you already know how to solve.
All right, on to example number 2. So, what's the new wrinkle this time? Take a look. Yep, it's that squared term. We've got a repeated linear factor, that x minus 1 squared. And believe me, that comes with its own special set of rules for how we break it down.
So here's the deal with a repeated factor like x minus 1 squared. Your setup has to include a term for every power up to that square. So you need a term for x minus 1 and a term for x minus 1 squared. Once you solve for all the coefficients, we end up with these three simple fractions. Now, the first two, no problem. They integrate into nice, clean logarithms. But that third term, the 3 over x minus 1 squared, that's different. You can't use a log there. What you do instead is you rewrite it with a negative power, so it becomes 3x minus 1 -2. Then you just use the reverse chain rule. You add 1 to the power, so -2 becomes -1, and then you divide by that new power. Easy as that. And that gives us our final answer, which of course we can clean up a bit with our log laws.
Okay, so we've seen the core techniques in action. Now it's time to put our skills to the test. Let's head to the proving grounds, the textbook exercises. We're going to dive in and tackle questions 3 through 6 from exercise 8E. Let's do this.
So we're jumping right into exercise 8E from the textbook. It's always good to see the problems right where they come from, you know? It kind of grounds us in what we're trying to do. First up is question 3.
But wait, before we even think about touching question 3, there is a golden rule, an absolutely critical first step.
Look closely at all the parts of this question. See how the highest power of x, the degree, is the same on the top and the bottom? That makes it an improper fraction. And here's the thing you cannot, I repeat, cannot use partial fractions on an improper fraction directly. The first step, and it is non-negotiable, is you must do polynomial division first. You've got to pull out a whole number part and get a proper fraction that you can actually work with. Okay, let's break down part A. First things first, we expand that denominator out to get x squared plus x minus 2. Then we do our division, x squared plus 2x plus 3 divided by that. What do we get? We get 1 with a remainder of x plus 5. So what this means is our big, ugly integral has now turned into the integral of 1 plus the integral of our new, much friendlier, proper fraction. Now we can unleash partial fractions on that second piece. It splits nicely into 2 over x minus 1 over x plus 2. From there, it's just a matter of integrating each little part, plugging in our limits of 3 and 2, and after a little bit of work with the log laws, we get our final answer, 1 plus ln of 16/5. Moving on to part B, and you're going to see it's the exact same playbook. And that's great, because this is how you build that muscle memory. We divide first to get the whole number part, we use partial fractions on what's left over, and then we integrate and evaluate. Seriously, the numbers are different, but the process is 100% identical. And that lands us right at 4 plus ln of 5/12.
And to wrap up question 3, part C is, you guessed it, the same drill one last time. Divide, partial fractions, integrate, evaluate. You can really start to see how this becomes a system, right? A reliable process. The final answer for this one is 2 minus ln of 2.
Now, question 4 looks a little bit different. And sure, you could factor that denominator into x minus root 2, x plus root 2, and use partial fractions, but who wants to deal with all those square roots? It can get really messy. There's almost always a more elegant way. Instead, let's just split the numerator. This creates two separate, much easier fractions. The first one, x over x squared minus 2, is a textbook f prime of x over f of x situation. And the second one, 3 root 2 over x squared minus 2, actually matches a standard formula for integrating 1 over x squared minus a squared. This is a fantastic example of how recognizing patterns can save you a ton of time and headache. After you integrate and plug in the limits, it all just magically simplifies down to ln of 3. Beautiful.
Okay, on to question 5, and now we're throwing some trigonometry into the mix. So here's a pro tip. Whenever you see trig functions all jumbled up in an integral like this, the very first thing that should pop into your head is, can I make a substitution here? And for this problem, the answer is a big resounding yes.
So check this out. If we let u equal sine of x, what's du? Well, it's cos x dx, which is exactly what we have sitting on top of our fraction. How perfect is that? This move just brilliantly transforms a really nasty-looking trig integral into a standard algebra problem, the integral of 1 over 9 minus u squared. Of course, don't forget to change your limits. Sine of 0 is 0, and sine of pi over 2 is 1. And from here, it's just a simple partial fraction problem. We break it down, we integrate to get the logs, we plug in our new limits of 0 and 1, and the answer comes out to a clean 1/6 ln of 2.
And here we are at question 6, this time with exponential functions. And just like we saw with the trig problem, the absolute key is to hunt for a substitution that's going to simplify everything. The obvious choice here, you gotta let u equal e to the x.
Okay, so if u equals e dx, then we know du is e dx. But wait a second, our numerator is e squared x dx. So what do? No problem at all. We just have to be a little clever and rewrite e squared x as ex times ex. Now we can make our substitution perfectly. The first ex becomes our u, and the ex dx becomes our du. So the whole numerator is now just u du. The rest of the integral falls along just as easily. We swap out the limits, e to the power of 0 is 1, and e to the power of ln of 2 is just 2. And look at that, we've done it again. We turned a complicated mess into a standard partial fractions problem, which works out to our final answer of 1/2 ln of 2720.
All right, we have battled our way through the textbook exercises. Now it's time for the final test. Think of this as a rapid-fire round of typical exam questions. This is where we see if we can apply these skills quickly, accurately, and, under a little bit of pressure.
Just take a look at these exam questions. At first glance, they might seem like 5 different problems, but they all share the exact same DNA. Every single one has a denominator with 2 distinct linear factors. And once you spot that pattern, you can solve them incredibly fast. I mean, let's just grab question 2 as an example. You've got a over x minus 2 plus b over x plus 1. If you use the cover-up method, you can find that a 3, and b a 1 in literally seconds, which means the integral is just 3 ln x minus 2 plus ln x plus 1. Done. See how fast that is? The same pattern works for all 5. This isn't about memorizing a bunch of answers. It's about training your brain to see the underlying structure so you can solve problems efficiently when the clock is ticking.
And there you have it. We're done. You have now seen exactly how to take these big, intimidating integrals and just systematically chop them down into simple, solvable pieces. This really is a genuine superpower to have on your calculus journey.
So, let's wrap this up. What are the key takeaways, the things you absolutely have to remember? Well, first, always check for improper fractions. If the power on top is the same or bigger than the bottom, you have to do polynomial division first. No exceptions. Second, you've got to identify your factor types. Is it linear, repeated, quadratic? Because that tells you exactly how to set up your decomposition. Third, keep your eyes peeled for a U substitution that can simplify your life before you even start with partial fractions, especially when you see trig or exponentials. And finally, brush up on your log laws because you'll almost always need them to simplify your final answer.
We have built such a solid foundation today. We've handled linear factors, we've dealt with repeated factors, and we've seen how to use substitutions to turn crazy problems into manageable ones. But all of this leads to a pretty big question, one we kind of hinted at with that very first example. What happens when you get those really tricky irreducible quadratic factors in the denominator? What's the full strategy then? Well, that sounds like a challenge for our next session. Thanks for joining me today.